Hello everyone. Let me first walk you through what we are actually trying to build here. This project is a full production planning framework and the goal is pretty straightforward. We want to simulate realistic manufacturing scenarios where we deal with bills of materials, I mean BOMs, calculate lot sizes, generate production schedules, analyze available capacity, and even simulate customer demand with things like ATP, I mean available to promise. And everything's going to be centered around a class that lets us test different planning strategies like make to stock or make to order and see what happens under the hood. Okay, you can see libraries here. We will use Streamlit, Pandas, NumPy, Matplotlib, GraphWise, and datetime, and of course Pulp for optimization. And here you can see. Okay, here we have a class, and this is the advanced production optimizer class. It's kind of the core of our system, and you will understand. And when we initialize it, we are just setting up some empty placeholders for the key structures we will need. Things like products, BOMs, routings, inventory, and orders. These will all be loaded in later. We are also preparing a spot for the actual production plan, which will be generated dynamically. Okay. So look at here. Here we have a method called calculate lot sizes. This is where we compute how to break up and total demand for a product into smaller manageable chunks or lots spread across a scheduling period. So the question we are answering here is, if I have to make say 500 units over a month, how should I divide that up into batches that are efficient to produce? We are begin by defining some constants. You can see the setup cost is 500 and the holding cost is 0.5. These are standard EOQ parameters. And then we assume a fixed production rate of 100 units per day. And using these values, we calculate the economic order quantity with the basic square root formula you can see here. And nothing fancy here, just the standard square root of our holding cost. And once we have that EOQ value, we figure out how many lots we will need. We divide the total demand by the EOQ and round it, but just in case it comes out as 0, we make sure to take at least one lot using the max 1 and dot logic. And then we calculate the size of each lot by dividing the total demand by the number of lots. Then we go into this loop where we build a list of lot dictionaries. And what are they? Each lot includes the product ID, the lot number, the lot size, the day it's scheduled to start, and the day it's expected to finish. The scheduled days are evenly spaced across planning window, and in this case it is 30 days, and the completion day just adds the production time needed for that lot based on the rate. And okay, now moving on, let's take a look at how we actually simulate a basic production schedule. So we have got this method called generate production schedule, and the idea here is to create a bunch of made up orders, kind of like a tested workload for products we want to plan. And right now it's set up for made to order, which means we are only producing when there is an actual request, not building up inventory ahead of time. And first we check whether we already have a production plan stored. Okay, you can see is none. and if it is still empty, we go ahead and generate it from scratch. We looped through two products, product A and product C, and simulate orders for a 30-day planning period. But we are not creating orders for every single day. Instead, we roll a random number for each day, and only about 20% of the time, because of that threshold here, it actually generates an order, and this keeps the schedule from being unrealistically full. Okay, and for each of these orders, we randomly choose a quantity between 10 and 100 units. Then we simulate the start and end times for the production in hours. And notice how we multiply the period by 24 to convert days to hours, and then we subtract or add some random offset so that it doesn't always start and finish right at midnight. That keeps things more realistic. We also give each order a due day, somewhere between 1 and 5 days after its assigned period. And once that loop finishes, we just convert the whole thing into a data frame and save it as our production plan. Then we return it so we can use it in other parts of the app. So this gives us a basic semi-random but plausible looking schedule. We can play it. Okay. Now let's take a look at how the sample data is actually loaded. This happens inside the load sample data function, and what we are doing here is creating an instance of the advanced production optimizer class that we defined earlier, right, and then manually populating it with a small set of sample data. So the first thing we define is a data frame for the product list. And we have got finished products like product A, product B, and product C. And then we also have sub-assemblies A and B plus a basic raw material. Okay, and we are adding a short description for each just to make it more readable in the UI later. And that's okay. So then we move on to the bill of materials, or the BOM, right? Actually we call it BOM. This part defines the structure of each product, what components are used to build what. For example, product A uses sub-assembly A and raw material, and product B uses sub-assembly B and raw material. Same thing for product C, it combines both sub-assemblies. Then we have got the sub-assemblies themselves, which also depend on the raw material. Okay, and each of these relationships includes a quantity, which is how many units of a component are needed to make one unit of the parent item. These numbers are made up for demo purposes, but they reflect how BOMs are structured in real production systems. Once we assign all that, we just return the optimizer object with everything loaded. And I hope it's okay. Okay, now let's look at how this all comes together in the Streamlit app. When we run the main function, we start by configuring the app layout and giving it a title. Pretty standard setup. So we load the sample data we just talk about and store it in a global variable called optimizer. After that, we list out all the product IDs so the user can select one from a drop-down menu, right? You can see here. And this is a product they will be planning. Once a product is selected, we have got an expander section for visualizing the BOM. And this is where things start to get a little more interactive. Why? Because we are using graphics to draw a visual representation of the product structure. So for whatever product the user picks, we generate a node for it. Then we walk down the BOM recursively, pulling out the components and drawing edges with the required quantities as labels. And I hope that's okay. And here you can see this add nodes function handles that recursive traversal. For every component listed as a child of the parent product, we add a line in the diagram and keep going down the chain if that component also happens to be a parent in the BOM. Once everything is drawn, we show the graph directly in the app using SD graphics chart. And this is helpful when you want to quickly understand how many levels your product has and how all the parts are connected. And I hope this is okay for you. And here we have a calculation part. Let's look at this. And here we will check out how the load sizing calculation is actually shown in the app. So inside this load size calculation section, we ask the user to enter the total demand for selected product. Default values is 500 units, but they can type in whatever number makes sense for their case. And we call our earlier function calculate load sizes using that demand value and a scheduling period of 30 days. This gives us a list of production loads, each with its own scheduled day, load size, and expected completion. Then we plot this visually as a horizontal bar chart, and each bar represents one load. The y-axis is the load number, and the width of each bar shows how big the load is, while the x-axis shows the day it's scheduled to start. So this makes it easy to see how the production is spread out across the planning window. And here Gantt part. It is another section for the Gantt view of the production schedule, and this is focused on the make to order scenario. So we call the generate production schedule function with that manufacturing type. If it returns a non-empty data frame, we go ahead and plot it. Again, we use a horizontal bar chart, but this time each bar represents a single job in the schedule. The length of the bar shows how long that job takes from start time to end time, and the position on the y-axis shows which product and which period it belongs to. And the y-axis labels combine the product name with the product period, so we can quickly identify when and what we are producing. The x-axis here is in hours because remember, earlier we converted periods into hourly values when generating this schedule. It gives a clearer picture of production timing at a finer scale. And ATP part waiting for us here. This one is pretty simple but still useful. And what is that? Here the idea is to let users enter a requested quantity and a delivery rate and see if the system can commit to fulfilling that order by that date. Right now this is just a mock check, so we simulate whether the system can fulfill the request with a random outcome. And if the condition passes, we show a green success message that says yes, we can deliver the requested quantity by the selected date. Otherwise, we show a warning that says the requested date is not double, and we suggest an alternative date by adding a random delay of a few days. This kind of check would usually be backed by inventory and supply chain logic in a real-world system, but here we are just demonstrating the flow and UI. And capacity part is here. Let's look what's happening. Okay, This part of the app estimates how much of each resource is being used every day and whether any resource is overloaded. We start by defining a basic set of resource capacities. So we have got machine 1 and machine 2 and assembly line and labor hours. These are the max available for each day, just fixed values for now. Then we have a helper function called estimate resource usage. You can see. And based on the product type, this function tells us how many units of each resource that product would need. For example, product A needs 2 units of machine 1 and 3 units of labor. Product C uses machine 2 and assembly, and if it is any other product, we just assume 1 unit of machine 1 as a fallback. That's okay, and we loop through all the scheduled jobs in the production plan and apply that logic you can see here. We track usage per day and per resource using a dictionary. So for every job we figure out which day it falls on, check what resource is needs, and keep a running total usage across the planning period. And finally, what's happening? We compare the daily usage against the resource capacities. If usage is greater than the capacity, we flag that day and that resource as overloaded. The result is built into a list of dictionaries where each entry shows the resource, the day, how much was used, what the capacity was, and whether there was an overload. And overload part is okay, and we will use this later to display a table and maybe plot a chart showing where bottlenecks or overloads are happening in the plan. And I think it's okay, and we can continue, and let's look at this DF capacity part. Line 175. Okay, now once we calculate the resource usage and whether there is any overload or not, we display that info in a simple table. That's what DF capacity holds. It has one row per resource per day with how much was used, what the capacity was, and whether it was overloaded. If you find any rows where overload is marked true, we raise a warning in the app saying overload has been detected. Otherwise, we show a message confirming that all resources are within limits. So the user gets immediate feedback on whether the current schedule is realistic from a capacity point of view. And just below that, we generate an optional line chart. You can see here what is that. This chart helps visualize how usage compares to available capacity across time for each resource. So for every resource in the table, we plot 2 lines, one showing how much was used per day and one showing the constant daily capacity. The dashed line is for capacity. This way, any spikes that cross the dashed line clearly indicate an overload. It is a simple visual, but it's useful for spotting bottlenecks that are not obvious in the raw numbers. And now, let's say someone wants to compare 2 different production strategies, make to order versus make to stock. That's what this next expander is about. And here we simulate both strategies using the same method we saw earlier. The difference is the argument we pass in. First we simulate MTO, I mean make to order, and then we simulate MTS, make to stock, I mean. Each one returns a different schedule, and we are not go deeper into what makes them behave differently yet. We are just comparing how many lots are created in each case. The MTO approach usually leads to fewer, more scattered orders, while MTS tends to be heavier and more front-loaded. So if you are seeing big differences in the number of orders, that's what's going on. And finally, we have got a short analysis on how delay affects inventory pressure. This section starts by generating make to order schedule just like before. Then we calculate delay for each job by comparing the actual completion time with the due date. If the job finishes earlier than its due date, we treat delays as zero, no early penalties here. And we compute the average delay across all jobs. That's shown right above using ST metric. Okay, you can see here. And it is easy to spot whether we are running behind overall. Then we also display a risk level for excess inventory. The logic here is pretty simple. If the average delay is more than 2 days, we mark inventory risk as high. Otherwise, we keep it low. Again, this is just a rough indicator, but it is good enough for simulation purposes. And main part here, and I think you are ready for Streamlit. And let's look. Okay, welcome to our Streamlit dashboard. So once we run the app, this is what it looks like on the screen. And at the top we have got the title Advanced Production Planner, and right below that a short description of what this dashboard actually covers. You can see, I mean, things like bomb explosion, lot sizing, ATP checks, and basic capacity analysis. And let's scroll. The first interactive part of the app is this drop down right here. Select a product to plan. Here you can see product A, B, C, sub-assembly A, sub-assembly B, raw material, and so on. Okay, that's okay. I mean, let's stick with product A for now. And once we select a product, we can scroll down and expand the section called lot size calculation here. By the way, here you can see a bomb graph, right? You can close and you can open it, and I hope it's clear and you can see full screen. Anyway, let's continue what I'm saying. Okay, lot size calculation. This is where the user enters the total demands for the selected product, and here we have entered 500 units for product A. Once we submit that, the app runs the EOQ based lot sizing logic and gives us a visual output like that. And what we see here is the result of that calculation. This horizontal bar shows the size and timing of the lot. In this particular case, we only have one lot since EOQ and demand ended up aligning that way. So we see lot 1 starting from day 1 and running all the way to around day 500 on the timeline. This gives a quick visual feel for how the production is spread out. And okay, let's look at here. Gantt schedule view for make to order production. This chart is built using the randomly generated schedule we saw earlier in the code, right? And each colored block here represents a job that's been scheduled for either product A or product C. And if you look at here, I mean on the left hand side, the y-axis shows the product and the period. So for example, we have got things like product C 29 and product A 16, and on the x-axis we are showing time in hours. So this is a pretty straightforward Gantt view where you can quickly see which product is being made at what time and how long each production run takes. And the layout makes it easy to spot overlaps, idle periods, and even clusters of productions if they happen to show up. And the color coding just helps differentiate the jobs, but it doesn't carry any extra meaning in this case. Okay. And ATP, and let's see what's happening. Available to promise. What this section does is let the user input two things: how many units they want and when they want it delivered. So in this case, I have entered a quantity of 75 and selected a target delivery date. And what is that? April 25 and 2025. Once we have filled those in, the system gives us an answer. Can we deliver these on time or not? And as we can see here, it says yes. 75 units of product A can be delivered by the date we picked. This message is showing up in the green because the system was able to fulfill it. Keep in mind, right now, this is just a simulated response. It uses a random condition behind the scenes. In real production setting, this would be backed by inventory levels, production capacity, and confirmed schedules. So be careful for this. Okay. Diving here, moving down to the capacity analysis section, this is where things get a bit more operational. What we are doing here is checking whether any of the resources used in production have been overloaded of any given date. Okay, the table lists out each resource, for example, machine 1, machine 2, labor, and assembly, along with how much of that resource was used on a specific day, what its daily capacity is, and whether or not that day was overloaded. So looking at the data here, we have got some days where machine 1 was used for 20 or 15 units, and the available capacity is 16. Right, you can see. And same with labor. Some days go all the way up to 40, which is right at the limit, but still we are not exceeding the capacity in any case. That's why the overload column is showing empty checkboxes, and the green message at the bottom here confirms it. No resource overloads detected. And this gives us a basic sanity check before we move forward with the production plan. And if any of these boxes had been checked, we would need to look at the schedule and either push some jobs to different days or increase capacity if possible. And capacity is done. Okay, let's look at this. Okay, and the chart showing daily resource usage versus capacity. This is a line plot that helps us spot overloads visually. Each solid line here shows how much of a resource was used on a given day. So for example, the here blue line, here, what is that? Machine 1. Green is for labor, purple is machine 2, and so on. The dashed lines are the capacity limits for each resource. Okay, so the orange dashed line here, what is that? Here is the limit for machine 1, red dashed for labor, and so on. If any of the solid lines were crossing above their respective dashed line, that would be a clear sign of overload. But in this case, everything's staying with limits, which matches what we saw in the table earlier. So this chart just reinforces the idea that the schedule is currently feasible. strategies. Okay. Now scrolling down a bit more, we have got the strategy comparison section. These compares make to order and make to stock strategies in terms of how many lots each one generates. In this run, both strategies ended up creating 8 lots, so they are the same here. But depending on how the schedule is randomized and what parameters are set, these can vary quite a bit. So this is just a quick check to compare workload under each approach. And it gives us a starting point if we want to evaluate different planning styles. And the last section is delayed and inventory impact panel. This part tells us how much average delay there is in the schedule and how that affects inventory risk. So right now we are seeing that the average delay is 0 days, which is ideal. That means all the production jobs are finishing on time or earlier, and as a result the excess inventory risk is marked as low. Now if delays started creeping in, say we had a bunch of late completions, this risk indicator will switch to high. That's just a way of highlighting that inventory may start piling up or orders might miss their due dates. It's a simple summary metric, but a useful one for getting a quick read on how healthy the plan looks. And thank you for listening.